So in this lecture, we have to deal with some topics, and then we have to discuss about Carnot's engine. And after that, we will go in the second law of thermodynamics. So, so let us start with two definitions which are important for today's lecture is um, thermal expansivity and isothermal compressibility. So thermal expansivity, as the name suggests, is thermal expansivity, which is represented with the symbol alpha and is equal to 1 by V, that means per unit volume, del V by del T at constant pressure. So the change in volume as you change the temperature. So if you increase the temperature, there will be expansion. That's why it is called thermal expansivity. The next parameter is isothermal compressibility. And again, as the name suggests, it is at constant temperature, compressibility. So it's at constant temperature and the symbol is beta and it is negative of 1 by V del V by del P at constant temperature. So with these two parameters, so isothermal compressibility is that how do you compress? You apply pressure, so you do it at constant temperature. So, well, in order to find out the relation of one variable with another variable, never you should change the third variable, okay? Because the effect of the third variable will not be able to, you will not be able to isolate that. So anyways, that's the definition of isothermal compressibility. And now let us take internal energy. But before taking internal energy, let us also understand the definition of what is known as specific heat. So specific heat is represented by symbol C, and it is the change in heat per unit change in temperature. So when this is at constant pressure, then you call it Cp, and when it is at constant volume, you call it Cv. And these two are not same. Okay. So for the same amount of change in temperature at constant pressure, the amount of heat which will be taken will be different from the amount of heat which will be taken if you do not allow the change in volume. So let us take internal energy U as a function of temperature and volume, and we are free to do that. So the change in internal energy can be written by chain rule of differential as del U by del T at constant V dt plus del U by del V at constant T dV. And by first law of thermodynamics, we know that du is equal to dq plus dw, where dw is minus pdv. Okay. So with this, let us try to find out using this relation. This is equal to that relation. So let us remove the middle guy, which is also our national aim. So in order to find out dq by dt, which we need to find for specific heat definition, so then if I have to write what is dq by dt, then what I can do here is equal to del u by del T at constant volume. So dt is already gone, plus P dB will come here. So I'll have P plus del U by del V at constant temperature, and this will be dV by dt. Okay. So this is our general form of change in heat, which is specific heat. Now let us impose the condition of having pressure constant. So that means Cp. So Cp will be equal to, so what will happen when the pressure is constant? This is okay, right? So I should have, well, for the sake of simplicity, I should first impose volume as constant. We can do pressure constant also, but it will be better. You will see why. So when we take volume constant, then dV by dt term goes away. This term goes away. So second term goes away. And what remains is just del U by del T at constant volume. And by definition, Cv is what? Cv is dq by dt at constant volume. So what do you see? That the change in heat or unit temperature is exactly equal to change in internal energy when the volume is constant. So that is Cv. Okay. And now let us impose constant pressure. So when we do that, let me start here. So then that will be equal to Cp when I put here, when I put pressure constant. So that will be equal to, and this term you see that is equal to Cv plus I have pressure plus del U by del V at constant temperature, and I will have del V by del T at constant pressure because I'm imposing that. Okay, and then I can write Cp minus Cv divided by del V by del T at constant pressure is equal to P plus del U by del V at constant temperature, and del V by del T at constant pressure is here, is equal to alpha V. So this I can write as alpha V, right? And then by doing, so I can also use this relationship, but for that relationship, getting from del U by del V to del V by del P, I need to introduce entropy, which we are not doing right now. So then we will put that part later, but right now I can just give you the final expression is that Cp minus Cv after converting that will come to Tv alpha square by beta. And this is a generic equation, and for ideal gases it becomes Cp minus Cv, which you have read in your 11th and 12th standard, is equal to nR, where n is the number of mole and R is the universal gas constant. Okay, so this is a special condition, and this is a general condition, which comes from more general condition, which is this. Okay, so in this general condition, you put pressure constant, and then you get this, and you put volume constant, and then you get that. Okay, fine. So now let us go to the main topic of today, which is Carnot's engine. And in Carnot's engine, there is a lot of history with Carnot. It's actually Carnot in French. I'm not very good in French, but then it doesn't matter. So Carnot's engine and the story of Carnot, we are not going to discuss that. But there is a very beautiful Carnot's theorem. So Carnot's engine is basically in the space of pressure and volume, and you have two isotherms and two adiabats. Well, it is not really vertical, it's like this. And so this is at T1 and this is at T2. And you see that these are isotherms because the temperature is same, and these are adiabats. And isotherm, they follow PV is equal to constant because temperature is constant. So for ideal gas, you can say that PV is equal to nRT and T is constant. So it becomes PV is equal to nR, which is constant. And for adiabats, it is PV to the power gamma is equal to constant. So it has a steeper slope, and that is what basically Carnot cycle is. But we have to discuss about Carnot's theorem. And Carnot's theorem says that the efficiency of all reversible cycles are same, and it is always greater than efficiency of any cycle which is not reversible. Okay, so that's the theorem. So this is irreversible. So that is the theorem of, that is the Carnot's theorem, and the proof of this theorem is very elegant, although very complicated. So in order to make the curd out of the brain, let us do that, and let us see if we are able to do that, if I am able to do that. So we'll come back to this because I need space for it. So I will write down here nr is greater than or equal to, or I can simply, well, yeah, okay, fine. And now let us take two reservoirs. Reservoirs are two bodies. Okay, so you can imagine two rectangular slabs which are made forcefully constant at two different temperatures. So these are basically two reservoirs, heat reservoirs. So you can have, like, for example, your environment and a closed system which has a different temperature. And then let us consider an engine which takes some heat. So T1 is greater than T2, and so it takes some heat, it produces some work, and it gives away some heat. Okay, so let us call it Carnot's engine, and Carnot's engine is a reversible engine. Okay, so let us call it C. So this engine C takes the heat QC1, gives the heat QC2, and of course by first law of thermodynamics it should be understood that QC1 is greater than QC2, isn't it? Because you can't take, it will be very weird if you take less amount of it and give more amount of it and also do some work. That is going to be some magical stuff. So without proving, we will disprove it. But the speciality of this Carnot's engine is that you can reverse it. Okay, you can reverse it and it does the same thing. In that case, we can't say it's not that QC1 will become QC2. So now let us add another hypothetical engine, H. Okay, and this engine H takes QH1 heat from here, and it gives out QH2 heat, and it also produces work, which is WH, and this is WC. Okay, and this is what Carnot says, but we will, like we do always, so we will say that the opposite is true, and then we will see that no, it is not true, and hence proved. So we will say that this irreversible engine H has higher efficiency than the reversible Carnot's engine. Okay, so this is what we are starting with, and then we will find out that it is not true. Okay, so how do we do that? In order to do that, let us now combine these two and make a complicated engine. Because Carnot engine can be reversed, what we will do now is that we will reverse it. Okay, and we will make an assumption. So we will reverse it. The amount of heat remains same, and what we are assuming now that the amount of heat which is being produced by this hypothetical engine is equal to the amount of work is equal to the amount of work which Carnot engine consumes when it runs in reverse. Okay, so we are saying that WH is equal to WC. So now let us look at this thing from which we started with. So what is eta H? Eta H is the efficiency of hypothetical engine, which is equal to the work hypothetical engine produces divided by the heat input, which is QH1, right? And eta C is the work which Carnot's engine either produces or consumes divided by the heat which it takes, which is QC1. Okay, so when it was running in forward direction, then we made this assumption. Okay, now we are saying that WH is equal to W, and we also said that eta H is greater than eta C. This is not true. This is what we are imagining, that well, let us not go there. So we assume that this is that. And if this is true, that WH is equal to WC, that means whatever heat it is, whatever work it is doing is running the engine in reverse direction for the Carnot's engine. So in that case, what will happen? This is greater than that, and because this is equal to that, right? So what will happen then? So we'll have QC1 will be greater than QH1, right? Isn't it? So QC1 into WH will be greater than QH1, or can we come to this conclusion by itself? So let us see that efficiency of hypothetical engine is, say, X. Okay, and so if this number is higher, because the upper part is same, so if this number is higher, eta H is going to be smaller than eta C, which cannot happen, right? So that means QH1 is smaller than QC1. QH1 is smaller than QC1, correct? So this is what we are getting from this. Okay, fine. And so this is now reversed. QC1 is greater than QH1. That means the heat which is going in reservoir T1 in the complicated engine is larger than the heat which is taken from that reservoir. So now you know that this is against Kelvin's and Clausius both statements, right? The amount of heat, there is no work which is going anywhere else. Okay, so it is taking less heat and giving more heat, right? Isn't it? But let us now do that. So how much heat is being taken by this complicated system? It is QH1 minus QC1, right? This is the amount of heat which is going in. It is taken away from reservoir T1. The amount of heat which is given to reservoir T2 is QH2 minus QC2, right? This is the amount of heat which is being given to the system, taking from one reservoir to another reservoir. Work is being consumed. One engine is producing something which is taken by the second system. So now applying first law of thermodynamics, it is going to be equal, right? Because energy cannot be created nor be destroyed. So QH2 minus QC2. So these two are going to be same, isn't it? The amount of heat which you take, you have to supply that much amount of heat. Otherwise, there is some balance. And there is no balance because there is no additional work anywhere. And QC1 minus QH1 is this one. QC1 minus QH1 is opposite of this, right? So I can write it as QH1 minus QC1. So QH1 is smaller than QC1. So this is less than 0, right? So that means this is going to be less than 0, right? So, and both of them are going to be less than 0. So what are we coming to? We are coming to the conclusion that the amount of heat which you take from the hot reservoir, QH1, you're taking heat from the hot reservoir, which is QH1 minus QC1, is less than 0. That means you are actually giving heat to the hot reservoir, right? Isn't it? That's less than 0. So you're giving heat to the hot reservoir. And because this is equal to that, that means this is also less than 0. So that means QH2 minus QC2 is the amount of heat given to reservoir 2. That means, and which is less than 0, that means you are taking heat away from reservoir 2. So what is happening is now that you are taking heat, there is a net heat, which is this, which is equal to that. You're taking heat from cold reservoir and giving to the hot reservoir. Okay. And in doing this, you are not doing any work. Neither a work is being done on the engine nor the work is being done by the engine on the surrounding, and therefore there is no net work which is remaining, which is unbalanced. So that means that it is against Kelvin's statement and Clausius' statement that you cannot give heat to a hot bar and take heat from a cold bar without altering the environment. And this is against the statement of second law of thermodynamics of Clausius and Kelvin both. And therefore this is wrong. So this cannot happen. So what can happen is that eta H must be less than eta C or equal to. So you take no heat from hot and you give no heat to cold. And then whatever you do, it doesn't matter. So the theorem of Carnot's that any reversible engine will always have higher efficiency than any irreversible engine is proven. Okay, and with this I'll give you an exercise to do. Is that now what you do is that you make this hypothetical engine also reversible. Okay, and you reverse that also. And by doing that, you will prove the other part of Carnot's theorem is that the maximum efficiency you can have is from reversible engines, and all reversible engines will have same efficiency. This part of Carnot's theorem can be proven with the same example once you make this also reversible. Okay. So that I'll give you as an exercise to be done. And with that, I will close this chapter today, and we'll start with a different state property in the next lecture. Okay.